Let's see, is that a big molecule or small one? It's a big one. So we should get a pretty big number for our molar mass.
44,026.
44,000? Right. You know what you got?
Yeah.
You know what you guys got? 44,000?
Still better.
Okay, so the molar mass, when you solve for molar mass here, the molar mass is 44, what was it, 44,000? What?
926.
926?
Yeah.
And the units are going to be in? Okay, so we look at this, let's see, we have atmospheres here. That's going to cancel out. We got liters here. We got, let's see, degrees Kelvin there.
Grams.
We have the moles there. We have grams. Now, molar mass should be in units of, okay, grams, this should be in grams per mole. Yeah, so we should get big numbers. That makes sense. 44,000. If you got something like 4 or 40, that's too small for a protein.
Let's check the back of those.
So let's see. Now, in biology, are you guys using for molar masses of biomolecules like Daltons and kilodaltons? You guys use that? I think a Dalton is the same as a gram per mole, and a kilodalton is 1,000. 1,000. So this is like 44, almost 45 kilodaltons. You guys have to Okay, now it says in the next part, what is the actual molar mass of the protein? So actually what we're doing here, I think for part A it says calculate the molar mass. They didn't use for the I value 21. Okay, so they're just using I equals 1. And then for the actual molar mass, this will be the actual molar mass because you included the number of particles in solution. Okay. And actually, but there's one more thing. Okay, I just thought of this. Note that this protein is Na20P. So note that that molar mass includes the 20 sodiums. So if we would look at the protein only, yeah, we want to subtract the 20 sodiums. Okay, so this is the molar mass of the Na20P. So for the protein, the P20 minus, this is going to be this number, 44,926, minus 20 times the molar mass of the sodium ion, which is equal to 23? 23. So you see, 23 times 20 is 460, so 44. 926 minus 460 is 44, 460. 44, 466. So this is going to be the mass of the protein. Now later on this semester, we're going to talk about acids and bases. And we'll actually apply that to amino acids and proteins. So we can actually change the charge on this protein by changing the pH. Okay, so we'll learn how to do that. Although we won't look at these big proteins, we'll look at amino acids. They'll have these charges of minus 20. So again, this is what we've talked about before. You guys as scientists and engineers want to control nature. You want things to do the things you wanted to do. So one way to do that, for example, if you don't want the charge to be minus 20, you can change that charge by adjusting the pH. Okay, so we'll learn how to do that later on this semester. Okay, let's go on to the next slide. Oh, so let's take a look at reverse osmosis. We were just talking about osmosis. So let's see, so we can purify water by various methods. One way is by reverse osmosis. Now, what's another way to purify water? Okay, so water purification. Okay, so one way to do that is by reverse osmosis. We'll talk about this in a few minutes. What's some other ways to purify water? Heating it up and then... Okay, so heating and filtering. So when you heat it up, what does the heat do?
The heat kills all the pathogens.
Yes, this kills bacteria. And then when you filter it, what does that do?
Dirt.
Yeah, it removes. Yes, this removes the solids, suspended solids in there. Okay, so, and then there may be some other steps too. So heating is one way to kill bacteria. Another way to kill bacteria is by using ozone. Okay, so that's another way to do that. Another way is by irradiating with UV light. Okay, so these are different ways to kill bacteria. Did you hear that story? This was, I think, last year, the year before. Although there's a lot of water on Earth, there's not really much drinkable water. So water's got to be purified to be able so you can drink it. So there was a county, actually there is a county in Southern California, and what they were doing, they were taking toilet water, and I think they went through 7 or 8 steps to make that toilet water drinkable. Yeah, so they did a thing like 2 different filtration steps. They used ozone and UV to kill bacteria. Reverse it. Yeah, there's no water up in the space. So that's what the water company does too. So when the water company pipes water from the water supply to your faucet, they've got to do a few of these steps to make sure it's drinkable. So, although I have a degree in chemistry, I'm not quite sure if I would want to know if my drinking water came from toilet water. Okay, are there other ways to purify water? Yeah, actually, charcoal is another. So this you use like activated carbon, charcoal, as another filter. Yeah, so this is actually a good way. Rather than just filtering through filter paper, you've actually filtered through activated carbon. The activated carbon will absorb certain substances. For example, it absorbs some chlorine or maybe some organic compounds. You can actually buy like a water filter which will go on your water faucet, and that filter will contain activated carbon. So it removes, I think it removes iron and chlorine and some organic compounds.
What about iodine pills?
Yeah, iodine pill. Yeah, iodine is another way to kill bacteria. So we'll put that in. Because that's a good oxidizing agent. Or as for that matter, another one is bleach. So bleach is the same bleach we use at home, which is used in swimming pools. And so these are all different ways to kill bacteria. So what's another way to purify water? You did something like this in the Chem1A lab.
Evaporation.
Yeah, distillation. Did we talk about distillation in Tuesday's lecture? You know, you're lost at sea and you don't want to drink the seawater, so you would set up that little distillation apparatus and it will still purify the water. Are there any other ways to purify water? Yes, so I think these are probably the most common ways. Okay, so let's talk about reverse osmosis. Okay, so let's see. Oh, so we talked about 3, gosh, we should just read the slide. 3 major ways to accomplish desalination. They're distillation, which we wrote down there, freezing, and reverse osmosis. Now, how does that freezing process work?
combine cells.
The water molecules.
Yeah, so we know that freezing converts a liquid to a solid, so it converts the liquid water into ice. But how is that going to separate, say, salt from the water? So how is that going to work? Yes, how is freezing temperature involved? So note that, see, in distillation, what property are you using to separate the water from the other substances? You're using boiling point. So freezing point can also, so you should go in, instead of heating up, you're just cooling it down. Okay. So for example, if you cool it down to, what temperature would you need to cool it down to remove the water, in theory? Yeah, 0 degrees. Yes, that's what pure water will freeze at. So what will actually happen is that you would freeze the water, the whole thing freezes, and then what would you do to remove the water or the impurities?
Well, if the water freezes to an ice cube, just take the cube out, right?
No, but if you just have the cube, you'll also have the impurities in it. So how would you separate the impurities from the water? Rolando?
Is it because of density?
Yeah.
Because of the ice is less dense or?
Yeah.
No, yeah, because it would float on.
Yeah, so you could actually do that. Because that's based on a difference in density, that's how you can separate the one from this. Because this is actually the same way that silicon is purified to make the silicon wafers to make electronic circuits. Okay, because that's what they do is they take sand, which is silicon dioxide, and then they heat it up. And then what they do is they put this pure silicon crystal in there to seed the solution. And actually what